Morning everyone. Just want to share something. Okay, so this is ANSYS Fluent. So it's a solver which is used mostly when you're dealing with fluids. So like we know, ANSYS is a very broad, it's a very big in the broader software. It has a lot of things. So I just want to show you guys one of the elements of ANSYS and how you can use it. So just sit back and relax. So just learn one or two things. I'm just trying to show you the interface, what's involved and everything. Okay, so as you can see here, this is the Fluent Solver. Okay, so I'm just trying to run a simulation by injecting particles. So as you can see here, it will tell you the type of injection. So at injection point is where you want to let your droplet enter the particular experiment you're trying to solve. So there are points. So there are different types of injection. So you have group injection, surface injection, volume injection, cone. You also have plain orifice atomizers. So there are times where you want to inject particles through an atomizer. So there are a lot of types of atomizers. You have pressure swirl, air bursts, flat fan. Yeah, so for this example, I will just pick surface. So I want to inject particles from the surface according to the model. So if you want to inject from a single point, you can pick single, but here I will inject from the surface. Then here you choose which surface, from which surface are you trying to insert your particles in. So my surface is inlet. So I want to inject from the inlet. Okay. Then here you can choose the material which you want to inject. So what kind of materials am I trying to inject? So you pick here. There are a lot of elements, so to speak, which you can pick, and anything you can pick, anything here, anything you want, depending on the experiment. So for mine, I've already specified the material for this example, so no need of doing this because I've already defined the material which I will inject. Okay, so you can specify other parameters here, like the diameter, the temperature, so the particles you're injecting, what is the condition of them, for them entering. So you can change, for example, the total flow rate. Let me say I'll inject at 1 kg per second. Yeah, so you can put your flow rate there. Then temperature, I can say okay, it should be entering at 100 degrees Celsius. Okay, then the diameter of each particle you can specify. For this example, just leave it the way they are. So again, here the surface option. From the surface, I want to inject my particle using a normal direction, so it should be entering normal. If you want, you can put normal, meaning they will be entering straight down. Okay, so you can specify magnitude of velocity. You can say okay, they will be entering at the velocity of 1 meter per second. Okay, so next, what else can we do here? There is so uniform distribution. So I like using this. So ANSYS, like I've said, it has a broader interface. So most of these things are coming from the theory. So before you have to read about these theories. So the diameter distribution, there are a lot of theorems about this. So the best way you can learn this is by referring to the menu. So you can go to the menu and get a glimpse of what is Rossum Lamla. Yeah, Rossum Lamla theorem like diameter distribution, so you can just get a grip. You can refer to the menu. Yeah, so for this example I'll use this one. Then you have also here, so here again, there are a lot of things which, like momentum exchange, heat exchange. So all these are theorems which you have to read depending on the particular application. So you read. So particle rotation, should the particle be rotating, you can specify if you want. Breakup, so after injecting, the particle has to break up into smaller particles. So we're trying to simulate something related to spraying. So if it breaks up, it will form smaller components. Okay. Next, so you can choose the breakup module. So I like using this one. So refer to the menu on these components and the formula related to the KHRT model. Okay. So here you have the dispersion model. Most used, the highly used one is discrete random walk. Okay. Then you have parcel. Parcel will just leave it to standard, and UDF initialization, no need to change. Okay, so when you finish, you click OK. So we were creating an injection. So that's what we were doing here. We were creating what? Injection. So this is our injection. Okay. So you can specify these interaction with a continuous phase. So for example, you're injecting air and some other liquid. You want them, you mix them, okay, and see the behavior at the outlet. So if there will be, at every point there will be air and water throughout your system, you pick this interaction with a continuous phase, because what this does is you have two elements, let's say air and water. Even at the outlet there will be air and water, so you need to set that these two will be in a continuous phase. So continuous phase, you have one, so let's say you're injecting water and air. Okay, water and air. So air is flowing and water is flowing. So they are in a continuous phase. Even at the output, the interaction is still there. There is no point in that experiment where you have water and the air separate. So they have to be interacting, exchanging. It can be temperatures. Yeah. So this is the same principle which heat exchangers use. Okay. So we're done there. So this is my model. I'm trying to inject particles here, and they observe their behavior at the outlet here. Okay, so this is just a simple experiment. Okay, so here, like I've specified already on the elements, I've specified already that I'm trying to use water for this experiment. Then I have also my insert particles. This I didn't change by default. Okay, so you can see the properties of each. So if you want to delete, you can delete here and insert a new one. Okay, so for the material of this body, I've specified to be aluminium by default. Okay, so what else should we do? Then boundary conditions, like I said, I've already specified. So boundary conditions, for example, let's say inlet. So inlet, you can change here if you want the inlet to specify the flow rate. If you want to specify the inlet as pressure, you can easily pick here mass flow rate. You can pick here the type. But in this example, it's a velocity inlet, so we're specifying the velocity. So momentum here, you specify the velocity at which we'll be injecting our water particles. Okay. So here you can change if you want If you want hydraulic diameter and intensity, that's the most common used, you can just change it. Okay, but for this example, just use the tolerance, intensity, and turbulence ratio of this by default. Okay, then here thermal. Let's say you want to inject particles at a temperature of 100 degrees Celsius. Okay, so you just insert 100 degrees. Then DPM, this is a discrete phase model. From the inlet, how do you want the particles to behave? They have to escape. Escape meaning leaving, so you specify. If you want them trapped, you can pick trapped. If you want them reflected, you can easily pick reflect. Okay, so it's escape. Next, you specify for, you come to the walls of the tank, these walls. Okay, so the walls, you come here, edit. The walls, we don't want our material to be sticking to the walls. So how do you do that? So the walls, if they are moving, you can specify moving. If they are stationary, you pick stationary. Okay, so for this, you can specify here the flux. If you have the flux, wall thickness, heat generation rate. Yeah, so there are other applications where you have to specify these properties. But for this example, the walls are what is stationary and they don't dissipate any heat. So we don't want the walls to contribute anything. So enable wall particle heat exchange. So this is using heat exchangers. Yeah, so the walls were the most thing which I wanted to emphasize is here, discrete phase type. So here we know the walls. If you want the walls to be trapping the particles, you can just pick trap. If you want the walls to particles to escape from the walls, you can pick escape, but they have to reflect, meaning the particles don't have to stick to the walls. Okay, so after finishing, you click apply, then you close. Okay, then you go to outlet. So outlet in this example is a pressure base. It's a pressure based outlet. So you can specify the pressure, but I'll just leave it. It's better leaving it by default, but you can change here if you want to write an expression for the pressure or it's a constant. Yeah, you can do that. Okay, that's a topic for another day. Okay, so you can change also the units. If you want a pressure in other units, you can easily go to units here, then you go to pressure, so you go to P, where is pressure? Okay, so this is pressure. So there are these units here. You can change. You can check the atmosphere, PSI, all these other units, other types of pressure units. You can also define your own if you want. Okay, so that's about changing units. Okay, so basically the outlet temperature, we want these particles to have ambient temperature. So the ambient temperature by default is 26.8. So temperature is in degrees Celsius, but if you want it in Kelvin, you can also change. Okay, so what do you want the particles to behave at the outlet? Should they escape? Do you want them trapped? So let's say you want them to escape. Okay, so you click OK. Okay, so we've specified the boundary conditions here. This is the most critical part of this solver. So after that, what do we do next? Okay, we have specified other things like reference frames, cell division, open on it. Materials we've already specified. So energy is on. So you switch on the models, the energy has to be on. If you want to specify the temperature, you switch on the energy equation. So you have to click here if you want to specify the temperatures. Okay, then here viscous standard. So this is just a solver. You choose the model which you want to solve. Yeah, so like I said, ANSYS has a lot of so like there is the implicit This is where viscosity, if you know your solve, you don't want viscosity effect, just pick inviscid. Laminar, yeah, so you have those Reynolds numbers. So Reynolds numbers less than 2000, you can use laminar. So yeah, depending on the question, you can pick. So the best is read about these in the menu, ANSYS menu, and see which one can be used for a particular example. So for here, we're using the K epsilon equation 2. Then we're going to use enhanced wall treatment. Okay. Then here we're just going to use the standard model. Okay. These others no need. Okay, so just click OK. So energy, the model, then also discrete phase. This is when you want to inject, you need to switch it on. Okay. This is where I started my video. Then materials, you can specify materials. So fluid, you specify which fluid. So if you want to specify, or let's say you want to add a new material, you can just click here, create. Then what type of material do you want to add? If it's a solid, you pick a solid. If it's a fluid, the fluid. Then you click here. Then you choose from the list. These are fluids. So you can choose any of these. And if you don't have, you can just use a chemical formula, you define it. Okay, so that's about the material. Okay, so what else? Okay, so I think when you're done there, you can go to these others, will leave them as they are by default. So in other videos to come, I'll be explaining bit by bit. So this was just a quick or a brief layout. Just wanted you guys to be familiar with the layout. So you have the domain. So under domain, you have all these areas here like units, information, display. So if you want to check the quality, the mesh. So because first of all, before we come here, you need to draw the diagram like this one and mesh it, then name the inlet, outlet, walls, all that. So we go in step by step. So for this one, just wanted you guys to have a picture of how the Fluent Solver looks like. Okay, so you have physics. So under physics, these you have discrete phase, which are already here. So it's the same whether you use this setup or this here. Everything looks the same. So functions, you can define a function. Yeah, you have all these and solver. So solution. This is where now before you run the simulation, you need to initialize. So initializing, let's do that. So initialize, let's say number of iterations for initialization, let's pick 20. Then you, okay, so no need to change anything, and just click apply. So you can pick whether you want hybrid initialization or standard initialization. Then when now you define the number of iterations for initialization, you can click initialize here. Then it will run. Okay. So you have a console here. It was running, as you can see here. So whatever you do, you have a window here which will show you the initialization. Okay, and whatever you are doing to the model will appear here. So in case, for example, you clicked somewhere and you are lost, so you can restore. You can easily restore you can restore the appearance by just clicking here to take you back to the original way it appears. Okay, so next we have initialized. Now we have to calculate. So you can either come here, calculate, or you can just run it. You can go here, calculate. So you pick how many iterations you want this to run. So for this example, just pick, let's say 600. Okay, 600 iterations, so you can run. So you click run. Okay, so it will start running here. Okay, so like you can see, it's running. So it says the residuals 14 point execution, we've ran into an error. So meaning they have to be, it has failed to complete. So these kind of things happen. So when you run into an error, you check whether your meshing was properly, or if you've picked the correct models. Yeah, there are a lot of troubleshooting methods which you can do. So for this example, I didn't want to do anything like that, so let's try to reduce the number of iterations and try to run. Okay, so troubleshooting is so it's still failing. Okay, so there has to be something wrong with it could be the machine or other things. Okay, so like I said, for this video there is no need to, I didn't want you guys to like get you much involved into this. I just wanted to show the layout. So, and unfortunately my simulation is failing to run. So yeah, so there are a lot of things which you have to do, which I have to make another video and show you guys. Okay, if you run into an error, what could be the problem, steps and stuff. So yeah, so hope you guys have seen. Before you run a simulation, you initialize. Okay, so after initializing, that's when you can run your simulation. Okay, so let me try change. Okay, let me try something. Okay, see, try to initialize again. Let's see. So like you can see, it's running, and then later on it stops. Okay, 14 point. Yeah, so it's just cutting. So I think I'll show you guys in another video how you can work out and solve this error. But you can do a lot of cool stuffs here. So for example, after running, you can go to, so you can check your results, you can check the contours. For example, you can go to contours and see how the particles are moving. Okay, so you can check, for example, contour lines. You can pick, okay, I want the contour lines for the velocity. Okay, the contour lines for the velocity. But it's best if you specify, there is one element which you have to specify. Okay, so you have to specify the wait a minute, let me check. Okay, so for you to visualize properly, you need to create some plane. So you create a plane first of all. Okay, so let's cancel this one first. So you create a plane. So you can see, you can create a plane in the middle like this, or you can change the direction. Let's say ZX. So you can move the plane. So let's say XY. You want a plane like that. okay, and it should be at the middle so you can create. So after creating a plane, now that's when you can create your contour line. So these are just visualization methods of visualization. So you can pick velocity, let's say, so you pick the plane. You want to visualize from the plane, then you save and display. Okay, so this one is showing you that your maximum velocity is 1.53 10 raised to power 4. Okay, so you can visualize it nicely here. You can modify your contour. So you can modify your contour. You can create a contour for the temperature. How does temperature move? Total pressure. Yeah, so this is the contour too. So this contour, so this is our contour, first contour. Okay, so it will just help you visualize what's happening in the diagram. Okay, so let's remove the global ranges, auto range. Okay, so let's say from 0 to 100. So from 0 to 100 is showing you. So you can tell, for example, you're designing something, you can visually see, okay, so my highest velocity will be in this region. So even when designing, there are a lot of components when you're designing. So there has to be that consideration to say, oh, so our velocity is weakest up to this point. So when fabricating this kind of equipment or this kind of apparatus, we need to take into account that up to here, so you can now take some other necessary precautions. Okay, so not only can you visualize the velocity, you can visualize temperatures. Okay, for example, temperature, how is the temperature distribution up to the outlet. So you can also see the vectors, so the vectors of velocity. So you can see the velocity vectors. Okay, so let's close this one. So this is just showing you the velocity vectors, like how are the velocity moving in all the directions. So let me just, okay, there's something I didn't specify nicely, so I'm supposed to pick the plane here and not this guy. Okay, so it has to be on this plane. Okay, so you can see how the particles are moving. Okay, so that's about the vectors. You see how they are moving, so you can tell, okay, the particles are moving this, meaning they will hit the wall. Where are we having a circular motion here, then you advise your team to say, okay, if we pick this injector, we'll have particles moving in this fashion. So make sure you know how to consider the walls. So for example, the walls, at the image you have a higher velocities circulating, like moving in a circular portion. All that has to give you some meaning to say, oh, here we have the highest concentration of velocity. So that's how you can visualize. You can also do, there is also path lines. So path lines are also used to visualize how particles move. So you can say, you can pick the plane and also hit display and save. Okay, so close this. So path lines, to show you now how the particles move. So path lines just show you how the particles are moving inside. Okay, so you can see the power of Fluent Solver. So this is used in multiple designs. Can be cooling towers, mixing chambers, also combustion chambers, yeah, radiators. Can use Fluent Solver. There are a lot of also other applications like even heat exchangers. They use this principle. Okay, so yeah, so I'm glad you guys have an idea of how to most of the things which Fluent Solver can do. So it's one of the coolest softwares. So this is ANSYS. Okay, yeah. So thank you for watching and have a lovely day. I think I'll make another video where I'll show step by step. For example, what I've done for this video, step by step from step 1. What do you do here up to this? So I just wanted to give you the overall outlook of how ANSYS works and how you can use ANSYS Fluent Solver. So thank you.